Welcome. Let's go. Well, I love this session. It's launch, learn, and repeat. And we actually came here. We launched the satellite. Great. Well, actually, this was moving in there. We got the satellite up. What are we going to do now? Well, we're going to make a new one. We're going to reuse a lot of stuff from this satellite. We're going to really focus on payload. From now on, our life is going to be very easy. Well, no, that's not the case. It's getting difficult. There's problems. Components become old. Actually, there is a huge one. I see the... We might have regulatory changes. And, well, I'll see later what's the problem. But it's some stuff that we didn't really expect. So in that sense, we had to change our own plan a little bit. Well, what is the zero debris policy, basically? I love the term. It's called policy. So it's actually something you might not really have to care about. Unless, there's a couple of unless there. You signed the Zero Debris Charter, so you're binding yourself to respect this. That's great. You're actually doing something with ESA. For example, fly your satellite. Then you'll have all the technical officers checking you to make sure you really respect this policy. Your national agency might actually say, well, this policy is a great idea. We actually want you to follow it. So it now turned into a regulation. That's great. ESA didn't do it, but our national agency did that. Well, potentially the same problem or feature will come in case the future European space law, which is under discussion, actually mandates something similar. And it is actually being discussed to follow this policy actually as a regulation. Well, again, I'm not really against. Sustainability is really important. So I'm the engineer and I'm teaching students to do engineering. So actually we are the guys that need to deal with this policy. And that's the point. I'm going to tease you a little bit about this just because I want to get to the point later on why or how can we make science. Well, the policy requires you to have maneuver capabilities. It actually says it in a very nice way, recurrent maneuver capabilities, but it doesn't really define what recurrent is. You have to maneuver plenty of times. And also, if you are in LEO, you have to do that. If you want to do formation flying, you really need to have that, and that's one problem. If I go further, well, if you have operated your spacecraft, you know what a conjunction is. You're going to get a lot of messages. You have potentially to react within 12 hours. That might actually be a complicated problem. You have to avoid a conjunction. That basically means whatever means you use, you need to dodge another spacecraft quickly. The other thing that I want to highlight is maybe you'll have to provide your precise ephemeris also often and quickly. That's important because, of course, the risk of collision depends on how well you know where your satellite is and the other satellite is. So if you know it better, your collision risk is maybe nothing, so you don't need to care about. Last but not least, ephemeris should come within a day of deployment. You all remember your deployment day. Where is my satellite? There's about 100 being deployed at the same time. Who am I? Well, that needs to be fixed quickly, one day. This is what the policy requires you. Now, again, it's not really my work. The European Space Agency has thought a lot about this, and this comes back to you as satellite designer, and it came back to us, actually, as designer, when we were making our own mission. And actually, we had to think a little bit how to change stuff. So, now, getting back to the topic of this presentation. Can we really make science? Now I'm bringing a lot of problems. Well, can we make science? Can we contribute to that? Well, debris, probably you heard, is going to be my focus. Can we fix space debris by launching yet another 2 satellites? Well, the answer is probably no. But probably there is something we can do. Well, if you look at what I said before about the Zero Debris Charter, there's a lot of breadcrumbs there that will lead you to what we can actually do as science with what these satellites could be capable of. Well, the first problem, or the last problem to make my life easy, I need to know precisely where my satellite is. Precisely. What does it mean? Well, TLEs, 1 kilometer, 3 kilometers, 5 kilometers. That might be difficult if you have 2 objects getting at a distance of a couple of kilometers, well, they're small, but yeah, the collision risk is not zero. If I know my position within few meters, well, my probability drops drastically. Well, drag estimation. What it is drag? Well, the atmosphere is slowing you down, and it is actually in LEO, where most likely all of you have been deployed or will be deployed, it's the strongest disturbance you will face. But how well do you model it? Well, that's the problem, because that influences your position. And last but not least, do we know atmospheric density accurately? And that's the other problem, because we don't. Or at least, well, there is a service provided taking measurements from European satellites, like Swarm, that you see there. This is actually the most accurate service we have so far. That's great. Data is processed once every month. So all the predictions you have are based on propagation of measurement, which are 1 month old. What you probably can guess is that your error is going to grow over time. So no matter how fantastic this prediction is, 1 month of forward propagation will add errors to it. The other problem is, well, they come once every month. So it's not that easy to use these predictions. So is there something that we can actually do there? Well, how do we get, let's start from the end. How do we do precise orbit determination? We can start from basically what's the best. As I said, Swarm is currently one of the best satellites we have. It's one of the prouds of my university because it's actually provided by a team from our department. Prediction accuracy, approximately 0.5 centimeter RMS. This is of course coming about a month late. Can we do that with one of these satellites? Well, in order to do that, you need to download all your raw GNSS measurements on multiple frequencies and then process it. Well, the download is 6 megabits, considering one station. Can we actually do that with one of these satellites? The answer is probably no, again. But can we take some commercial receivers to actually do maybe not everything we did before, but something a little bit less? Well, of course, receivers got smaller. The Swarm satellite GNSS receiver is actually this size. It's a toaster, a little bit more. Actually, I need to fit in that shape, and that's what we're actually building right now. So GNSS receivers, in order to do processing with actually using commercial GNSS receivers, but we need to add a separate layer for processing in order to adapt to the space environment, which mostly is a different dynamic model. In that sense, what we've been working on is actually an algorithm to potentially get down to centimeter level with actually dual frequency receivers. So that also together with processing on board can help us get into precise ephemeris with an accuracy somewhere ideally in the 0.5 meter. So that is already helping a lot in the debris problem. But, well, we talked about drag. That's the other important part where we are working on. How do we estimate drag? Well, we can model the satellite shape very accurately. This is what is done on Swarm. But actually, we still have something like 30% error, which we can't really have. That's the big problem. You really need to go and model the interaction of gases, and that's the problem. So how do you do the modeling? Well, you need to look at the inclination of surfaces with respect to the direction of motion. And what you notice is that that inclination can give you some information on actually drag. So now that's the second breadcrumb on what we can do actually with these small satellites. Last but not least, atmospheric density estimation. And now we come to the science. In order to do atmospheric density estimation, we need to know where we are very accurately. We need to know our drag very accurately. Well, as I said before, if you want to use drag predictions which are available, typically you need long-term propagation, weeks to months in advance. That's where the error grows. So potentially I might survive with predictions, or actually measurements, which are less accurate but much more timely. Can I do these calculations on board? Of course, not with the accuracy that Swarm can do, but can I then download those? That might give you few hours of lead time, and at that point, it might still be useful. So, in that sense, what do I want to do? Well, I need to, as I said, the angle between the satellite panels and the direction of motion is important, because by varying that, I can actually measure drag more accurately. And this was proven actually on Swarm, but they could only do one single measurement in the whole mission lifetime. What if I have two satellites? What if I have two satellites with two different attitudes, flying in different configurations? Can I use them to correct actually my drag estimation using the two satellites? Now, again, I have two satellites. If I know the drag, can I compensate the drag on both by measuring density using one and applying the density on the second one? They are very close by. So actually the atmosphere is the same. Does my orbit estimation improve? Yes or no? This is basically proving the algorithm that could be used to actually improve the estimates on other satellites and actually lead to a lower collision risk. So putting all these things together that came from a law or from a change of regulations, there you go. Finally, we got to the point. Meet the Delfi twins. There are actually two, It's not just one, and you have problems with your glasses. There's two satellites which look pretty much identical. Well, whenever they will be in the deployer, they will look like that. So they will be hooked up to each other, attached rigidly. We will only deploy them together. But at a certain point, well, we need to communicate with them. So we'll get the antennas out so we can operate both spacecraft hooked up onto each other. This is the first stage. Can we actually test the systems? Well, they're close by. Now, next stage, I might be a little bit out of power. Let me give a little bit more power by deploying the solar panels. Now I have a satellite which has a fairly large configuration. A lot of solar power, communication, actually two satellites next to each other. Now, bringing it to the full operational configuration, this gives me two satellites attached to each other, which are actually equipped with two GNSS receivers, as I said before. Well, look at them. They're bolted to each other. What if I measure the position with two of them? Can I measure the actual error in my GNSS algorithm? Can I debug that? Yes. I know the difference in position because I know the attitude, because I know they're bolted to each other. Now I can actually verify my GNSS estimate. We also carry laser reflectors because we want to verify independently the position. Now, finally to the point. I need two satellites that they need to separate, and they will separate on the same orbit because they've been flying together. This allows me to basically have control of the spacecraft only using differential drag. How do I achieve differential drag? Well, I can change the position of those panels. It's not literally just a spring. It's an active system with motors that allows me to configure drag. Now I have a surface with a varying angle with respect to the direction of motion, which I can use to improve my drag estimates. Well, the important thing, I need to keep them together, and that is the strategy now. So, I showed you the mission. Together with this mission, there's some other experiments that we will carry out. The first one is differential drag. Can I maintain the formation autonomously? Well, there is a legal issue. Of course, I don't want the satellite to sort of start to do stuff on its own and I have no control, but can I have them simply get the first one to increase its drag so that it gets closer to the second one? Now they're too close. Great, swap. Now the first one reduces its drag while the second one actually increases drag, and then they separate again. So I can get them close by. This is fundamental, so I can keep them close and I can do the same measurements. I can also, if you look at how I can change my drag more or less by opening the panels at different angles because it's an active system. What is my delta V that I can achieve actually? How quickly can I move away from an eventual debris? This is an almost completely passive system. I don't have a thruster that consumes 10, 20, 50 watts to actually obtain a delta V. I increase my drag. That gives me a response. And if the change is actually large enough, I can achieve tens of centimeters per second of delta V, which basically build up to a kilometer within half a day. That's actually what ESA wants. There is something more. As I said, if I want to know very well where my satellite is, I need to double check my GNSS receivers. That's why we fly laser reflectors. We went through the analysis considering nominal attitude for the spacecraft and actually also random attitudes for the spacecraft, that this is visible via the ILRS. So we can have independent orbital estimates down to centimeter level accuracy, so we can corroborate our GNSS measurements. That's one of the experiments. There's also a collaboration with the University of Santiago in Chile. They're actually fond of graphene, and they're using graphene transistors to do measurements. Again, it's not my expertise, don't ask about that, but these transistors could be used as the future sensors. But they are small, actually. Look, we are the perfect platform to demonstrate these kind of systems. So we're going to carry them together with us. We also have another experiment, which is also related to the upper atmosphere. This is in collaboration with the Radio Amateur Society in Belgium. They are interested in knowing if the atmosphere is ionized or not. Why? Well, because if all of a sudden there is an ionized layer, it becomes like a mirror reflecting signals up and down. So in that sense, this problem or phenomenon called sporadic E is actually a sporadic phenomenon. So sometimes the atmosphere is ionized, and we don't know very well how this works. Well, we have an idea, but not exactly. So the idea of this mission is to actually fly a beacon just above this layer, which basically means my beacon will be hearable from multiple stations on the ground, and there are networks that monitor this. So we will literally beep in their field of view, and at a certain point we will disappear. The moment we disappear, well, actually, if the satellite is still alive, I know that the atmosphere is no more transparent at those frequencies. And that's how we can actually contribute, again, to science. So, I ran a lot in order to fit everything and not to stop you from having a drink later. But I still have maybe some minutes for a question. It was a pleasure being here. Thank you very much.